Welcome to the deep dive. When you look at Earth from space, it's just striking, isn't it? That huge expanse of blue.
Dominates everything.
Right. Water covers over 70% of the surface. And it's not just pretty, it's, well, fundamental for every living thing.
Yeah.
Without it, nothing.
It really is the lifeblood of the planet. And, while we live on the land part, most of that water is actually in the oceans. It's this hidden, dynamic world. So much going on down there.
And that's exactly what we're diving into today. You've given us some great source material, and we're going to try and unpack some key ideas about the oceans.
Sounds good.
Our mission basically is to get a handle on some core oceanography concepts, how water moves around the globe, what the seabed actually looks like, temperature patterns, and of course, why it's salty.
Yeah, think of it as a journey into understanding this huge, vital part of Earth, often quite mysterious, too.
Okay, so let's start right at the beginning. All this water, where does it come from? And how does it move? The sources are clear. It's not just sitting still. They mention the hydrological cycle.
That's the one. The hydrological cycle, it's like Earth's giant water engine, been running for billions of years nonstop.
An engine, okay.
Yeah, it's all about the continuous movement, the circulation, exchange of water. On the Earth, in the Earth, above the Earth, it's shifting between liquid, solid, gas, all the time.
So it's not consumed. It just changes form and place.
Exactly. It's a cyclic resource.
Yeah.
Life absolutely depends on it. The sources highlight some key steps, like evaporation.
Water turning into vapor.
Right, mostly from the oceans, but also land, plants, everything. That vapor goes up, then it cools down, and you get condensation. That's cloud formation.
And clouds lead to rain, snow, that sort of thing.
Precisely. That's precipitation. Water falling back down. When it hits the land, some of it flows over the surface runoff, heading to streams, rivers, back to the sea.
Okay.
But, and this is really important, some of it soaks into the ground. That's infiltration.
Infiltration, seeping downwards.
Comes groundwater. That can flow underground for ages, maybe pop out as a spring, but eventually it finds its way back to the rivers or the ocean too. It's this whole interconnected loop. Evaporation, condensation, precipitation, runoff, infiltration, back again.
It sounds incredibly, well, comprehensive on a global scale.
Yeah.
But here's something interesting the sources mention. The distribution isn't even at all, is it?
Not even close. About 71% of all water on Earth, it's in the oceans, salty.
Wow, 71%.
Yeah. The rest, the fresh water, is mostly locked up in glaciers, ice caps. Then you've got groundwater lakes, rivers, even in the air, and, inside living things.
And there was a stat about rain on land.
Oh, yeah, pretty striking. Of the water that falls on land, something like 59% goes back up into the atmosphere pretty quickly. Evaporation, plants releasing water vapor.
So nearly 60% just goes straight back up.
Duh.
That connects to something serious.
Yeah.
The sources raise the water crisis.
It really does. The key point is the total amount of water cycling around stays roughly constant, right? But our demand for usable, clean water, it's just soaring. Population growth, industry.
Creates shortages.
Exactly. Water scarcity, not just in droughts, but is a constant issue in many parts of the world. And then there's pollution, which, as the sources rightly point out, contaminates the water we do have access to. It really makes you think, doesn't it? How do we collectively, individually step in, improve quality, conserve?
Definitely a huge challenge, tied right back to that fundamental cycle. Okay, let's imagine we could, drain the oceans. What would we actually see down there? Is it just miles of flat sand?
If only it were that simple. No, one of the really big takeaways from these sources is how incredibly dramatic and varied the ocean floor is. The basins themselves are these huge depressions in the Earth's crust.
Big depressions.
Yeah, low points. And while all the oceans connect, geographers usually divide them up, Pacific, Atlantic, Indian, Southern, Arctic, plus seas, bays, gulfs, smaller bits.
And how deep are we talking typically?
Most of the ocean floor is between, say, 3 and 6 kilometers below sea level, but flat is the last word you'd use. Think about the forces on land, tectonic plates crashing together, volcanoes erupting, sediment building up. Same stuff happens underwater, just on a massive scale. The ocean floor has the world's longest mountain ranges, its deepest trenches, and yes, some very large, flat plains, too. But it's definitely not boring.
Wait, the longest mountain ranges on Earth are underwater. Seriously?
Yep. Mind-blowing, isn't it?
It really is. So what are the main parts of this hidden landscape? The sources break it down, right?
They do. They talk about a few major divisions. First up, right next to the continents, is the continental shelf.
That sounds like the edge of the land, just underwater.
Pretty much. It's the submerged extension of the continent, relatively shallow, gentle slope, usually less than 1 degree. It ends at a point where the slope suddenly gets much steeper. That's called the shelf break.
How wide is this shelf?
Hugely variable, almost nothing in some places, like off Chile. But then you look at the Siberian shelf in the Arctic, it stretches out 1,500 kilometers. The average is maybe 80 kilometers. Depth varies too, maybe 30 meters down to 600 meters or so.
And what's down there on the shelf?
Sediments, loads of them, washed off the land by rivers, glaciers, wind, then spread around by waves and currents. And here's a crucial point. These thick layers of sediment built up over millions of years. That's where a lot of our fossil fuels come from.
Oil and gas. From ancient mud and sand on the shallow edges of continents. Wow, okay, so after the shelf break where it gets steep.
That's the continental slope. This is the transition zone, connecting the shallow shelf down to the really deep ocean basin. The gradient picks up significantly, maybe 2 to 5 degrees. It goes from about 200 meters depth down to maybe 3,000 meters. This marks the true edge of the continental block. You can find canyons and even trenches cutting into the slope.
And beyond the slope, down the real deep.
Then you generally hit the deep sea plain or abyssal plain. These are vast, gently sloping areas. Think incredibly flat, incredibly smooth regions, some of the smoothest places on the entire planet, actually.
Smoother than plains on land.
Probably, yeah. They're covered in really fine-grained sediments like clay and silt that have settled out over vast amounts of time, filling in any irregularities. Depths here are usually between 3,000 and 6,000 meters.
Okay, vast, flat plains. But then there are the extreme depths.
Right, the oceanic deeps or trenches. These are the real plunges, narrow, very steep-sided basins. They go significantly deeper than the surrounding abyssal plain, often 3 to 5 kilometers deeper.
So if the plain is at 6 kilometers, the trench could be 9, 10, 11 kilometers down.
Easily. Mariana Trench is the famous one, nearly 11 kilometers deep. They're usually found near the base of the continental slopes or along chains of volcanic islands, what we call island arcs.
And they're geologically active places?
Very much so. The sources make a key point. These trenches are linked with active volcanoes and strong earthquakes. They're hot spots for studying plate tectonics where Earth's crustal plates are interacting, often one diving beneath another.
Makes sense. Like zones where the action happens. How many are known?
Sources say 57 deeps have been explored to some extent. Most of them, 32, are in the Pacific. Makes sense. The Pacific Ring of Fire and all that.
And besides these big 4 divisions, the sources mention smaller features too. Minor relief.
Yeah, lots of other interesting stuff down there. You've got the mid-oceanic ridges, those massive underwater mountain chains I mentioned earlier, often with a rift valley down the middle.
Where new ocean floor is made.
Exactly. They stretch for thousands of kilometers. Iceland is actually part of the mid-Atlantic ridge sticking out of the water. Then you have seamounts.
Underwater mountains.
Yep. Individual volcanic mountains rising from the seafloor. Pointed summits, but they don't break the surface, can be thousands of meters tall. If a seamount gets its top eroded flat, maybe when it was nearer the surface, it's called a guyot.
A flat-topped underwater mountain.
Okay. Thousands of them, especially in the Pacific. You also find submarine canyons, huge valleys carved into the continental shelf and slope. Some are enormous, comparable to the Grand Canyon, often found offshore from major rivers like the Hudson Canyon.
So rivers carve canyons even underwater.
Or they're formed by underwater landslides, turbidity currents, complex origins. And finally, atolls. Those are ring-shaped coral reefs surrounding a lagoon, typically found in warm tropical waters. They often form on top of sinking volcanic islands.
Incredible. It's a whole other world down there. Plains, mountains, canyons, volcanoes. Now, what about the water itself? How does temperature work in this massive volume? Across the surface and going down?
Well, the main heat source is the sun, solar energy. But water, as you know, heats up and cools down way slower than land does. High heat capacity.
Right, so what controls the temperature patterns we see?
Several things. Latitude is a big one. Just like on land, it gets warmer near the equator and colder towards the poles because the sun's rays are more direct at the equator. Less solar energy per unit area as you go poleward.
Makes sense. Warmer middle, colder, top and bottom.
Pretty much. Then there's the unequal distribution of land and water. The northern hemisphere has more land, and land heats up faster. So northern hemisphere oceans tend to be a bit warmer on average than southern hemisphere ones.
Interesting nuance.
Prevailing winds matter too. Wind blowing offshore can push warm surface water away, allowing colder deep water to come up. That's called upwelling. It cools the surface locally. Wind blowing onshore can pile up warm water near the coast, making it warmer.
In those huge ocean currents, they must move heat around, right?
Oh, absolutely. Ocean currents are like giant conveyor belts for heat. Warm currents like the Gulf Stream carry tropical heat towards the poles, warming places like Western Europe significantly. Cold currents, like the Labrador Current, bring chilly polar water towards the equator, cooling nearby coasts. They're crucial for global heat distribution.
Okay, that covers the surface patterns. What happens as you go down deeper into the ocean?
Generally, temperature decreases with depth. Makes sense, right? Sunlight only penetrates so far.
How fast does it decrease?
It's not uniform. The temperature drops relatively quickly in the upper few hundred meters, and then the rate of decrease slows down a lot in the deeper water.
And there's a name for that zone of rapid change.
Yep, it's called the thermocline. It's a boundary layer, usually starting somewhere between 100 and 400 meters down, and it can be several hundred meters thick. Within the thermocline, the temperature plummets quite rapidly as you go deeper.
Like a thermal cliff underwater.
Kind of, yeah. Below the thermocline, you enter the deep ocean, and that vast volume of water, over 90% of all ocean water, is incredibly cold and pretty uniform in temperature, just a few degrees above freezing, near 0 degrees C.
So for most of the ocean, below a certain point, it's just cold.
Very cold. So in middle and low latitudes, you typically get this three-layer system. A warm surface layer, maybe down to 500 meters, the thermocline where it gets cold fast, and then the huge, stable, cold, deep layer.
But not everywhere.
Right. In the Arctic and Antarctic, the surface water is already close to freezing, so there's very little temperature change as you go down. You basically just have one cold layer from top to bottom, no significant thermocline.
Fascinating how it varies. Depends entirely on latitude.
It shows how sunlight, depth, and water movement all interact to create these thermal structures.
Right. Let's tackle the other big characteristic, saltiness. What exactly is salinity, and why isn't the ocean uniformly salty?
Okay, salinity. Basically, it's a measure of how much dissolved salt mineral salts is in the water. It's usually expressed as grams of salt per 1,000 grams of seawater, which we call parts per thousand, or ooh.
Parts per thousand, okay.
Yeah, and the sources note that anything above about 24.7 parts per thousand is usually considered seawater. Below that, it's typically called brackish.
What makes it saltier in one place and less salty in another?
At the surface, the two main drivers are evaporation and precipitation. Just think about it. High evaporation takes away fresh water as vapor, leaving the salt behind, so salinity goes up.
Like boiling salt water, the water leaves, salt stays.
Exactly. And high precipitation, lots of rain, adds fresh water, diluting the salt, so salinity goes down.
So hot, dry areas tend to be saltier, rainy areas less salty.
Generally, yes. Also, near the coasts, fresh water flow from rivers makes a big difference, significantly lowering salinity. In polar regions, freezing and thawing play a role. When seawater freezes, the ice formed is mostly fresh water, leaving the remaining water saltier.
Right, concentrating the salt.
And when the ice melts, it adds fresh water back, lowering salinity. Wind can move surface water around, affecting local salinity, and of course, ocean currents transport water with different salinities. And remember, salinity, temperature, and density are all linked. Change one, you often affect the others.
The sources mention some crazy high salinity levels in places like the Dead Sea.
Yeah, those are enclosed lakes with immense evaporation and little or no outflow. Dead Sea at 238. Ooh, Lake Van in Turkey even higher at 330. That's way, way saltier than the open ocean, which typically ranges between 33 and 37 parts per thousand.
33 to 37. So within that normal range, how does it vary across the globe?
Well, you see variations. The Red Sea, almost landlocked in a hot region, is very high, maybe 41 ooh. Estuaries or the Arctic can swing wildly, near zero sometimes, up to 35, depending on river flow or ice melt.
And the big oceans.
The Atlantic tends to be slightly saltier on average, maybe 36 ooh, with the highest levels in the subtropics around 15-20 degrees latitude, where evaporation is high. The Mediterranean is high because it's enclosed and evaporation is high. But the Baltic Sea is very low salinity because of all the rivers flowing in. Same for the Black Sea.
Lots of river water diluting it.
Exactly. In the Indian Ocean, the Bay of Bengal is less salty because of the Ganges and other big rivers, while the Arabian Sea is saltier, more evaporation, less river input. The Pacific shows variations too, generally less salty than the Atlantic.
So surface salinity is really a balance between evaporation, rain, rivers, and ice. What about vertically? Going down?
Ah, yeah, salinity also changes with depth, but unlike the surface, which is really variable, salinity deeper down is much more constant, more fixed.
How does it change?
Generally, salinity increases with depth, at least for a while. Because saltier water is denser, it tends to sink below less salty, less dense water. This helps create stratification, layers in the ocean. And just like the thermocline for temperature, there's often a zone where salinity increases sharply with depth. It's called the halocline.
The halocline. Okay, a rapid change in saltiness.
Exactly. It marks the transition between the variable surface waters and the more uniform, saltier, denser deep water. This density difference, driven by both temperature and salinity, is a major engine for deep ocean circulation.
Wow, okay, so we've covered the water cycle, the incredible hidden landscapes, the temperature layers, and now the salinity patterns in the halocline. Paints a really complex picture.
It really does. When you look at these fundamentals, the cycle, the seabed shape, the temperature, the salt, you start to appreciate just how dynamic and interconnected the ocean system is. It's not just a big tub of water. It's constantly moving, layered, interacting with the atmosphere and land. Absolutely critical for the whole planet.
Absolutely. It makes you realize how vital this huge blue area is. And just to wrap up our deep dive, here's something to think about, drawing on what we've discussed. We talked about underwater mountain ranges bigger than any on land, trenches deeper than mountains or high, vast plains, all hidden. It really drives home how much of our own planet is still essentially unexplored territory, holding who knows what mysteries down there in the deep, what discoveries are still waiting for us.